Yeah, so thank you very much for coming to the talk. I'm Stefano Albrecht, lead a research group at the University of Edinburgh. And today's talk basically consists of two parts. First, I'll tell you about our research in deep reinforcement learning, where we do a lot of work. And then I'll tell you about some more recent work in using LLMs for agent-based systems. But first, let me tell you a bit about our research group. We are the Autonomous Agents Research Group. We are currently about, I think, 17 or 18 people, which is PhD students and postdocs. You see some of them here. And really, all the work I'll be telling you about today is their work. So all the credit really goes to them. They're doing amazing work, a lot of work in reinforcement learning. And you can go to our website to find out about their names and about their projects. And please do get in touch if you have any ideas or want to discuss our papers with us. So it's a great group, really great people to work with. What do we try to achieve? We want to create autonomous agents that can accomplish tasks in complex dynamic environments. And so here I'm showing you some real examples that we're working on. We have a warehouse robotic automation on the left that I'm working on. I'll tell you a little bit more about this later. We have self-driving vehicles. This is a company that I helped to build up as well. And then the teamwork task on the right represents more generic, robots working together or agent-based systems. So what all these applications have in common is that you have to build highly capable autonomous systems that are able to situate themselves dynamically in this environment, process a huge amount of data, and make some informed choices to achieve a task. And something else that these applications have in common is that there is not just one actor, there are multiple actors that coexist in this environment, and they have to coordinate their actions in some important way in order to achieve their tasks. So we are working primarily in machine learning solutions, where basically machine learning algorithms for autonomous systems control and decision-making. And so as I mentioned earlier, this talk has two parts. The first one is about reinforcement learning. And then later on, I'll get back to large language models and some observations in this space. But let's start with the first part, which is about RL. Okay, so I think everyone knows what reinforcement learning is, so I won't spend much time explaining RL, but we'll tell you about the main problem spaces that we operate in. One is we care a lot about sample complexity and solution quality, so we want to learn as quickly as possible with the amount of data that we have and learn better models. We care a lot about robustness or generalization, many ways to define this, and I'll give you some examples later. We also care a lot about multi-agent systems. I mentioned earlier where there's more than one actor, and also various industry applications, including the ones you see here. So over the next few minutes, I'll try to give you a small sample of some papers that came out in recent years. And hopefully there's some basic ideas you can take away. And if you end up reading the papers, please get in touch. Okay, so let's, and so here are some venues where we typically operate. I think you will know all these venues, including the robotics ones at the end. So let's look at robustness and generalization to start with. Okay, so we are operating in reinforcement learning from pixels. Okay, so we have a camera, for example. We get to see, the environment, and we need to do some sort of control task. And reinforcement learning, as you probably realize, can be very brittle. There can be overfitting and correlate very heavily against the inputs. And in particular, so with vision inputs, you end up with basic policies that correlate very heavily against the pixels. And what happens is that you may be able to solve a control task like the inverted pendulum on the left here, or it's also called, basically the inverted pendulum. But then if you change a property, a feature in the environment, such as the color of the line and the cart, then the policy will fail completely, as you see here. And, that's even though nothing's changed about the control strategy. It's the same policy you should be using. It's just one feature that's changed, which is the color of the object, and then that's changed all these pixels. And now because we correlate against these pixels, we are completely confused. So we want to develop representations that are more robust and can generalize. So last year we published a couple of papers that developed this idea of disentanglement for reinforcement learning, which I think is a really important idea and leads to some interesting results. So let me explain what that means. In this vision, and this picture that I showed you just now in this example, where does this come from? Well, typically there will be some basic ground truth factors, such as floor color, wall color, object color, and so on. You will have these parameter values. And then once you set that up in your, for example, in your simulation environment, you will get to see these images that are produced as a result of these parameter values. But disentanglement basically means that that's not the end of it. We should not correlate against these pixels. Instead, we should try to recover these ground truth factors based on the observation that we observe. So we want to learn a representation. In this case, this is supposed to represent a vector that corresponds to the ground truth features. For example, we want to identify that there is such a thing as wall color and object color and so on. And the benefit is that if now things change in the environment, for example, we change the scale of the object or the shape, everything else will still remain defined and we will not basically fail. We can still continue to interpret these other values. We just have to adjust to the new values for these other ground truth factors. So that's a disentangled representation. And in this first paper that came out last year at iClear, we show this that you can achieve something like that using an auxiliary task, or basically auxiliary task for your loss function that we call temporal disentanglement, or TED. And I'm not going to bother you with the mathematical details or the architectures. I'm not going to talk about that at all. If you would like to find out how we do it, then please check out the paper. Instead, I'm going to jump right into some results. So we tried this with a bunch of different RL algorithms and also many different tasks. Here I'm showing you two different tasks that we tried. One is on the left with the cart, the inverted pendulum here, and one is on the right with the jumper problem. They're both from the DeepMind control suite. And to help you understand what this is showing, I'm not showing any results yet. So I'm just explaining the experimental setup. We are training the RL agent with a certain set of colors for the, for example, the robot. And then at this vertical dotted line, we make this switch in the environment where now we are testing the train policy and continuing to train the policy in different kinds of values for the color that we haven't seen previously. So what you will be seeing in a second is a bunch of lines for training returns over the number of time steps. And we test this with a bunch of different algorithms. And the red algorithm, we also test with the TED auxiliary loss that we developed in combination. And similarly, here's a similar setup where there's a jumping or walking task, and we train this in a certain set of values, and then we switch to different kinds of color values. And here we use a different RL algorithm that we then combine with TED. And so you can see as you train, everyone is improving more or less. And some more than others. And then there's this sudden change in the environment, and everyone is experiencing a massive drop in performance because they heavily correlate against the environment. But with the TED auxiliary loss, the first benefit is that you're not dropping quite as drastically, but also you will be able to recover much more gracefully with continued training after just a few additional time steps. Whereas some of the others fail to recover altogether, or they take much longer. And so we're able to show this across many different tasks, which I think is nice. But we didn't end there. We also analyzed the disentanglement factor with something called a beta VAE disentanglement score. And the best you can achieve there is 1. And we were able to show that we achieve better disentanglement as well in the representation. But this isn't perfect. You can do more. We didn't leave it there. There was another paper that came out at NIPS last year. And here we're now looking at the fact that there are also spurious correlations in the features in the environment. So it's not just the fact that these ground truth factors are fully independent, which is what we assume in TED. In fact, in many cases, there can be correlations between these different features, and we need to be able to account for them as well. So here's an example to show you what I mean. Let's say we have our cart control problem again here. And now let's say there's two different robot morphologies. One is with a longer stick and a smaller body. Then there's the green one here, which has a shorter stick and a bigger body and different friction coefficients, and it changes the optimal policy you need to employ. And then there's also different colors, which is what we saw earlier. So now the features affect the task relevant factors, which is the color, for example, but also they affect the task relevant factors, which is, for example, the weight and the friction coefficients. And if we are assuming full independence, and let's say we are training in a setting where most of the time we see these two combinations, blue and and a slimmer cart, or green and a sort of more chubby cart, then if you force independence, because these are highly predictive of one another, you will force the method to collapse them into a shared dimension in the representation. So blue in this particular card and green in this particular card. If you then go ahead and evaluate in sort of in a different setting where you see these kinds of combinations much more frequently, by forcing independence, you will fail in any generalization, and basically that's what we see when we tested TED and other methods as well. So we have a need here to also account for correlations, so that, for example, when we learn the optimal policy for this blue card here, and the only thing that changes is the color, the method will gracefully just transfer the optimal control policy from blue to green without actually changing how it controls the card. Similarly, if we remain in blue, but we are changing the robot morphology, then we should be able to switch to a different control strategy. Okay, so we want to account for disentanglement. This is about as much as a technical detail as I'll be showing you for the method, and then I'll just refer to the paper as well. But basically, we are integrating something called conditional mutual information into the reinforcement learning pipeline. Basically, on the right here, what you see with the Zs, this is the 2 dimensions in our representation that we want to learn. And they are dependent on the actual unknown state features that we do not have access to. But basically, in the paper, we show that you can achieve the disentanglement property that we care about by defining a particular conditioning set based on the MDP, which is basically the past representations and the past actions. So what this then reduces to is that we need to develop a method that can reduce conditional mutual information between these 2 features in our representation, given an appropriate conditioning set here. And that's basically what we show in the paper, how to do this in the RL pipeline. Again, let's look at some results. We call this a CMIT, which stands for Conditional Mutual Information for Disentanglement. Again, you can hook this up with any reinforcement learning algorithm and optimize this. And here I'm showing you, again, a few examples for control tasks. We tried this in many other tasks too, but I'm showing you just the subset here. And the regime for the training is what I showed you earlier, where we were changing from one diagonal to the other in terms of the probability of observing particular correlations. And so there's some really nice results. Let me walk you through what this shows. As usually, you have your training time on the x-axis and then your returns on the y. You have different algorithms that we tested, including SVIA that we then also combined with CMIT, which is our auxiliary loss. And if you just look at the green line across all 4 plots, this is basically our disentanglement objective. You see that on the vertical dotted line, when we have the drastic change in correlation, it seems like with the representations that we learn, we're not even affected by it. You can see that we don't have the catastrophic failure or reduction in performance that all these other methods have. Instead, the green line continues to train gracefully across this change. And basically what it means is that it's learned to disentangle these factors. When there's a change in colors and other correlations, it knows to transfer the control strategy. So I think that's really nice. And here I'm just showing you a video of what's happening. This is a video for the point in time when we make this change in correlation here. So the vertical line here. And first, I'm going to show you a policy that is not learned to disentangle. You can see that it's doing something weird in the training set, but in the testing set where the correlations change, it's completely failing to transfer. Whereas with the disentangled representation that we learned, you can see that from left to right, the same walking pattern transfers directly, even with the zero-shot transfer, with no continued training whatsoever. You can see it's the same walking style, which means the method is really able to disentangle the different ground truth features. And of course, you can then continue to train to polish it a little bit more again. So I think that's a really cool result. And a lot more can be done in this area. So I leave it at that. And if you look into it, please get in touch if you have interesting ideas. Next, I'm going to tell you a little bit about multi-agent research that we do. Here we now have multiple actors as opposed to just a single actor. And I'm going to give you just one example for a paper that came out at NeurIPS, I think 2 or 3 years ago, or maybe longer ago. I'm not quite sure anymore. But basically, here we are confronted with teamwork tasks, such as a toy version of a warehouse, or the StarCraft task, or other grid world style tasks where there's these multiple actors, multiple agents that coexist in the environment, and they need to work together to achieve a task. The difficulty that we add here is that there is sparse rewards, which means that most of the time these agents get zero rewards, which makes it really hard to learn. And only in very scarce defined moments when they've done something useful will they get a non-zero reward. So for example, in StarCraft, when they fully defeat the opponent team, and until that point, they get zero rewards. So it's a very difficult way to learn these tasks. We are proposing in this paper a very basic idea, which is what we call sharing experiences or shared experience actor critic. And I'm going to explain this with a very basic toy task here. So let's say we are in this grid world where there are these two agents, blue and red, and they have to move in the environment to arrive at the center point at the same time. And most of the time they will get a 0 reward, and only when they arrive at the center point will they get a positive reward. So it's, even though it's a toy task, you can see how there's an exponential factor here in the exploration. With the standard approach in multi-agent RL, which is called independent learning, every agent would just use its own experiences. So for example, the blue agent would only use its own trajectory here to calculate gradients and whatever, and then update its policy. And the basic idea that we observe here is, well, it kind of seems like a wasted opportunity, because surely the blue agent should be able to benefit from the experiences of the green agent as well, because they're solving a similar task. And that's what we're doing here. So let's say we are now looking at a situation where the green agent is using not only its own experiences, but also the experience of the other agent. So it's putting itself into the shoes of the other agent. And that requires now that we are fixing a distribution shift, because now we have a sort of off-policy data. It comes from a different agent, and we're doing this with basic importance sampling. And then basically what this allows us to do is to construct more robust local gradients in the way in which we update the policies. And so we don't do any fancy losses. We don't do any fancy architectures. It's all very basic stuff, okay? Nothing particularly fancy about the idea, but it turns out that practically it has some really interesting effects. So let's look at a version of this SMAC task here, where we are showing 3 baselines. One is for SEAC, which is ours, and then there's 2 baselines. The orange one is shared network actor critic, which is when all the data goes into one shared model that's trained together and they have identical behaviors. And then the blue one is just independent actor critic, which means that they are completely separate, own models and own data. There's no sharing. So you can see that here, purely with the ability to share data, we're already massively outperforming these other basic methods. And there's no change in the architectures at all. We're just sharing the experience. Similarly, for the warehouse task here, where you can see we're able to learn very quickly and also achieve a better, converge to a better local optimum in the joint policy space. But more interesting is to analyze what's going on here. And so that's what I'm showing here. So let me explain what this graph on the right shows. We took one of these tasks, this is a warehouse task with 4 agents, and we are plotting here for green basically trained the agents with SEAC, which is our algorithm, and blue trained the agents with independent actor critic when there's no sharing. And we are showing the individual agent returns, as they evolve over time. The thing that stands out here, and we observed this in many other tasks we tested, is that one agent begins to learn earlier than the other agents. And it's sort of, there's an unequal sort of learning happening here. And in fact, what we then observed is that this agent that becomes proficient earlier on in the process begins to deprive the other agent from experiencing the necessary data to catch up in the policy improvements. So they are unequal in the learning, and it means that sometimes agents can be left behind. They end up they are not able to explore effectively, and they end up in a worse joint policy space. Whereas simply by sharing data, we can ensure that we have a uniform learning progression. No one's left behind, so to speak. And that also enables us to explore better and end up with a better joint policy. So I think it's a really interesting observation here. And I think a lot more could be done to analyze what's going on here, potentially to extract some insights for how we should design these algorithms. Okay, here is just a video that shows like a trained joint policy for the red team. You can see that you're spreading out here. There's certain strategies going on. I'm going to skip over this because I think a lot of you know what's going on. Instead, I'd like to take a minute just to present the spectrum, which I think is interesting to think about. So we saw the blue line, which is no parameter sharing and no data sharing. So on the left, so here you have the benefit that you have distinct behaviors for your agents, but you do not have very efficient learning because you don't share parameters or data. On the right end of the spectrum, you have your full parameter sharing, which was the orange line. There we have a single model, and all the data goes into that one model, and all the agents share the same model. It means it's sample efficient, but it also means that we are not able to differentiate behaviors, which is bad for teamwork. Shared experience actor critic, which is what I just explained, is somewhere in between in the spectrum. Now we have the benefit that we can learn efficiently by sharing data, but because they're not sharing the models, they can still differentiate behaviors. And there's another paper that came out in ICML a few years ago where we actually showing that you can also selectively decide which of the agents should be sharing parameters to learn more efficiently. So please have a look at the paper if you'd like to follow up on that one too. Okay, so that's a little bit of the work in multi-agent. And now I'm going to tell you about some of the work in industry applications that I was able to build up with really amazing people. So I was fortunate to have personal fellowships from the Royal Society and Royal Academy of Engineering, which basically means I'm able to take off time from my professor position and build teams in industry. And the first thing I'm going to tell you about is a project that we're just working on with Dematic. Dematic are a gigantic warehouse and intralogistics company. They're putting money into developing robotics solutions for warehouse automation. And basically, we are developing with them, I think, the world's first application of multi-agent reinforcement learning in a serious industry-scale robotic environment. Basically, what we're trying to achieve with them is you can imagine a setting where there's a large warehouse, like an Amazon warehouse. There's all the shelves and all the items. And now there's a bunch of humans, which is what we call the pickers. They pick the items. And then there's a bunch of AGVs, which is the robots. They coexist with the humans, and they exist to serve the humans in order to sort of, receive the items that the humans pick and bring them back to a processing station. So there's a lot of benefits to doing it this way, and I don't have the time to explain the sort of the business idea just now, but I want to focus a bit more about, in terms of on the multi-agent RL solution that we're using here. So industry solutions that are being developed in this space tend to be very manual, engineering-heavy heuristics, such as assigning a predefined number of AGVs to individual pickers, and then they follow them. Or you have heuristics where human pickers are designed to predefined zones, and then there's the AGVs that need to decide how to travel and so on. So we now want to ask, can we use multi-agent reinforcement learning to fully automate this process of discovering meaningful strategies to manage the warehouse? And can we outperform these heuristics? That's basically what we set out to do. We are using a bunch of different warehouse configurations. The idea is that we should be agnostic to the specific warehouse configuration. So for example, these are all based on real-world customer warehouses. You have different scaling for standard warehouses. The disjoint one on the right here is actually a warehouse where there's a warm compartment and a freezer compartment at the back, and that's why there needs to be a very narrow sort of access channel so that all the freezing can be contained, basically. And so it creates some interesting challenges in terms of how they need to navigate. The approach at a very high level, the real product has a lot of other sort of enhancements, but at a high level, the idea is that we are now introducing this manager agent. So it's a hierarchical approach where at the top of, above the physical agents, there is the manager agent that gets to observe what's going on. And then at the ground level, there are the worker agents, which is the human pickers and the robot AGVs. Everyone has a policy. The manager agent is supposed to train a policy that can allocate tasks dynamically to the different workers. And the workers are concurrently training policies that are executing the tasks from the ground up. So they then need to coordinate how they execute these tasks. So I think it's a really interesting idea to think about this. The manager at this higher level has to learn how to efficiently manage its team, basically, based on how they operate in the task space. But the lower level workers have to use their local observations and the instructed tasks from the manager in order to figure out how to effectively solve the task. And then they hopefully arrive at a joint policy that is optimized in some sense. So that's as much as time as I have in terms of the method. Let's look at some results. So here's the small, medium, large, and disjoint warehouse that I introduced earlier. You're seeing a bunch of different lines. The horizontal lines are the two heuristics that I showed you earlier, follow me and pick, don't move. And then the ones that are improving over time are the multi-agent RL baselines. And the first thing that we can see is that we are actually outperforming these industry heuristics. And basically what we were able to see is that the RL algorithm is able to exploit particular properties of the environment to improve walking patterns, to improve coordination opportunities, whereas these engineered heuristics, they typically are limited by certain heuristic aspects, and they're not fully automated against the actual distribution of the data in terms of how they walk and operate. So I think that's very encouraging. And here's a video that shows you what's going on in action. So this is high-fidelity simulator developed by Dematic that includes all these different workers, and they're swarming out, and then they basically fulfill a constant stream of order profiles that keep coming in. So basically, lots of Amazon customers clicking all the time, orders coming in, and they're basically doing their operations, which is to go to the correct places, pick up the items, and the AGVs need to serve the human pickers to bring back the items to the workstations. So as a result of this work and other ongoing work, the company is now building a real-world prototype in Germany in a large test facility where they are replicating a customer warehouse like this with the robots and the humans. And it's now fully in the commercial pipeline as well. So I think hopefully in a few years' time, we'll be able to ship this out to some clients, which I think will be a really exciting impact opportunity. Okay. Well, I should say, again, a lot of credit goes to lots of people which are spread across Europe and the US, and they work at different sites and responsible for different parts of the project. Okay, so that was warehouse automation. And now I just want to take a couple of minutes to talk about another initiative I was involved in, which is self-driving in the UK. I'm not involved anymore because the business was bought by Bosch a couple of years ago. And after that, I phased out after a while. But still, I think it would be amiss not to mention what we've done here. So 5AI is a company in the UK. It was founded in late 2015 and quickly became a leading AV startup in Europe. AV is for autonomous vehicle, basically means autonomous driving. From the start, the idea was to build a complete driving stack, which includes perception planning, prediction, control. And in the later years, we had a big emphasis on the verification infrastructure as well. We were the lead partner for a UK government-funded project called Streetwise, where here's a vehicle from our fleet. We had a bunch of vehicles like this that we were operating in urban areas in London in two boroughs over a 20-kilometer route. And the company itself is itself a multi-agent system, has a bunch of offices in different places. And as I mentioned earlier, the company was bought by Bosch in 2022. Here's a vehicle, one of our vehicles driving in London. This is with a safety engineer. It's not touching the pedals of the vehicle, but has to be ready to disengage. And there's a lot of equipment inside to monitor the streams and do safety operations. Here is the same operation, but from the vehicle's perspective. There's the fused image at the top that takes into account different modalities to do global sensor fusion. And then at the bottom, you have two stereo camera feeds, one pointing forward and one to the side. And you can see there's the object detections. There's now, we need to wait at the roundabout. There's the overlay here that shows the local trajectory that we're planning. No one's waiting at the zebra stripe, so we can continue. This was actually a very easy situation to navigate. But what you can see is there's a huge amount of stuff going on here. And in fact, we are decomposing this problem into a bunch of different layers. That's why it's called the stack. You have to bring all these layers together. One is for sensing and fusion, localization, detection, tracking. Prediction and planning is where I mostly exist, and also control. And in our office in Edinburgh, we do a lot of work in prediction and planning. For example, we have these papers in trajectory prediction, goal recognition, optimal planning, explainable AI. I think a lot of people are interested in explainable AI. So unfortunately, I don't have time to tell you about all these cool pieces of work. Instead, I'm just going to point you to our website. And since I know that a lot of people are interested in explainable and interpretable AI, I want to point you to a new survey that we brought out, which I think nicely summarizes the literature in this space. So please check out the website. We're also hiring various places. Okay, so that brings me to the end of the first part. And I just want to take a couple of minutes to advertise some resources that I think could be useful. And before I get into the second part. So first, resources. In our group, we also have this blog, which you can find online on the URL here. And I think it has a lot of useful resources if you want to get into reinforcement learning. There's a blog post about tips and tricks for implementing deep RL, which is really important. I mentioned disentanglement. We have a new blog post that explains it. Unsupervised environment design, I think a lot of people are interested in. We have a new paper in ICML. There's also a blog post coming out today or tomorrow, and various other useful resources. So please go check it out. I think it will be helpful for a lot of people who want to get into this. And then we also have a large number of active code repositories, including eParmal. We have one of the original developers of Parmal here. And eParmal is sort of an extended version that sort of adds functionality and algorithms and so on. And it's sort of widely used now in the community. I think it's a good way to get started if you just want to plug and play. And it builds on the original Parmal framework, so it's compatible. Okay, so the second resources I want to share with you that I've recently finished writing a book, which is with my two amazing co-authors, published by MIT Press. You can get the book for free online, the PDF, and if you want to buy the print version, you can get that later in stores this year, I think in December. So this book gives you basically the full picture. It introduces single-agent RL, game theory, models and solutions, deep learning, deep RL, multi-agent RL, and so on. Gives you basically everything step by step, including practical aspects. It also comes with a code base that's designed to be easy to use, and some slides if you want to teach this in your course. And we already have a few universities that are actually using this now to teach. So I hope this is useful for you. Please check it out if you're interested in learning more about multi-agent RL. Okay, so that brings me now to the end of the first part. And now I'm going to switch over to the second part, which is where I want to tell you a little bit about this new initiative in our group where we're exploring how to use large language models to do agent-based systems. Okay, so this is a paper with a number of colleagues here. Let me sort of get started in terms of what we want to achieve here. So large language models, again, I think I don't have to introduce much. A lot of people know and use this already. There's an interesting history here, but now I think we're at a time where a lot of people are exploring all kinds of applications in terms of how to integrate LLMs or build apps and so on. In this work, we are in particular interested in using LLMs to enable robotic applications. And there's a few reasons for why we're interested in that. One is that we have a comprehension of complex task descriptions if they come in natural language. The ability to process human language instructions as well, and feedback, I think, is very desirable. It does not come easily with pure reinforcement learning approaches. There's this idea that there's this wealth of common sense knowledge that's extracted from the body of internet text, basically, and the ability to generate plans, basically, to execute in a robotic planning environment. So I think different labs have explored using LLMs in different contexts, but we are in particular interested in using this for planning tasks where we have to come up with a sequence of high-level actions to achieve a particular goal. And the environment that we're operating in is called the housekeep task, where we have a single robot called Fetch here. It looks like this. It's a simulated environment. The robot gets to see a picture like the one shown on the left here. And it's operating in a household environment that's shown like here, where we have a kitchen, a living room, a bathroom, and so on. There are a bunch of containers called receptacles here, and there are a bunch of objects that are spread randomly in the household. And basically, the robot's task is to clean up the household. So it will be instructed to bring certain objects into certain locations. That is basically the task here. There are a number of challenges involved here. We have a bunch of different rooms. They are partially observable. We have very limited observation in terms of what's going on. This is a long horizon planning task where sort of a longer sequence of choices need to come together in order to achieve the task. And there are many different combinations of objects and locations where they need to be stored. So there's a very large space of possibilities. The other issue that we identified is that if you do this straight out of the box, there's also a lack of personalization, which means there can be a misalignment of the user's preferences in terms of where a coffee mug should be located versus the general knowledge that is extracted by the LLM from the body, the internet text, basically. So we want to also infuse the planner with user preferences so that it understands contextual information better from the user. And we are proposing one particular way of achieving this. We call this LLM personalized, because we are personalizing it against user data. And it basically looks like this. In the first instance, to address problem one, which is the complexity and the scalability, we have an integration where at the center, there's this LLM planner. We use we have a way of constructing the prompt that goes into the LLM. The prompt has information about the environment, relationships between objects and locations, and so on. I explain that in a minute. And the LLM produces a sequence of high-level actions that need to be executed. These actions are then passed over to a controller that is executing them directly in the environment. In order to address this lack of personalization, we also add a combination of machine learning approaches, supervised and reinforced, where we are using user preference data to directly optimize the model parameters to make it more user-tailored. Okay, so just in a little bit more context, in a little bit more detail. First, how do we produce the prompt? It consists of three parts. One is the household state graph, which we construct basically as we explore the environment. Then there are the instructions, put object X into location Y, and so on. And then there's a couple of examples that give you the example format for the plan output. The context I just mentioned includes a description of the environment in the household, and we represent it as a graph, basically. So there will be nodes for individual rooms. As you explore the household, you will add nodes for different locations and for different objects that you encounter, and you can sort of build relationships, right? So pan 1 is currently in table 6, which is currently in kitchen 0. You can represent the environment in this particular graphical way. Once we have that, we represent that in language, and we combine that with the instructions and the example plan as the one big combined prompt that is then fed into the LLM. So it looks something like what's shown on the right here. Okay, so the first part is the sort of a language summary of the graph. Then there will be the instructions, put certain locations into certain objects into certain locations, and then also some examples to show the LLM what to output. Once that is received by the LLM, it produces these high-level actions. Go to pan 1, look at pan 1, pick up pan 1. So you see there's sort of a sequence of actions that's required. And these individual actions are passed to a controller that need to execute them in the environment. And we're just a customer to a predefined controller. Okay, so the next problem is the misalignment. So that's one of the interesting things, right? So we want this planner to understand the human's preferences. When the human says, put down the mug, we want the robot to understand that the mug is supposed to be in a particular location. And we achieve this with a two-phase optimization pipeline. One is using bootstrapping with imitation learning from user preference data. One is using a sort of an iterative reinforced self-training process. I won't have time to explain these things in detail, but I'll give you a pointer to the paper at the end if you're interested. Instead, let's look at some results. So here we have 4 environments, which are different sort of configurations of households with different rooms and objects and so on. We use evaluation metric, which is the success rate defined as basically have you placed all the items in the correct location. As the LLM engine, we use a GPT 3.5 turbo, and we use a small number of demonstrations and the self-training in order to do the user fine-tuning. So let me show you a video just to see what this looks like in action. Here we have first the agent is exploring the household in order to produce this environment graph. So it's now understanding the spatial relationships and so on. Now it's supposed to pick up the sweetener, which is on the table here. It's going in the correct room. It's looking at the sweetener, picking it up. Now it's understanding that it moves into a different room. There's a particular location where it's basically delivering the sweetener. That's basically what it looks like. It's focused primarily on the high-level actions, which are executed by a lower-level controller. But quantitatively, it looks like this. So I'll show you the data in a second. Let me first explain what the columns mean. We have seen 1, 2, 3, and 4 in the columns here, which correspond to the 4 different households. We have 3 different baselines, which we compare against. They come from the literature, existing planners. And then we have ours, which is based on LLM Planner. And then we use 1 improvement step with imitation learning, and then additional improvement steps with the iterated training. So to show you the results, you can see that we very significantly outperform these other approaches from the literature, which corresponds to a much higher success rate. So these numbers correspond to success rate, meaning the correctly placed items and locations. Okay, so just in summary, you can find the paper if you scan the code here. There's also the video you can check online. And again, please get in touch if you have any thoughts about the paper in terms of directions or anything that occurred to you. Please get in touch. So now I'm getting to the last part of the talk, and I think I'm hoping this will lead to some interesting conversation. So what are my personal observations about the state of research in LLM-based agents? And there's actually a number of observations that we made collectively in my group, but I just want to share 3 in particular that sort of stood out to me. Okay, so 3 observations. The first one, from what I can tell, having read about 20 papers now in this space coming out in the last 2 or 3 years, I think they all follow essentially the same general recipe, which works like this. At the center, you have your LLM engine. For example, we used GPT 3.5 Turbo. You can use other LLM engines. Then there's a very significant amount of effort that goes into prompt engineering. So basically that means how do you put together a large piece of text, which is the prompt that goes into the LLM planner, that tells us what to do and how to output the stuff, the context that it needs to know, examples and so on. So often these papers have this like large amount of effort where they explain in detail, all this engineering. It's fairly ad hoc, really. It's in our case, for example, we use a graphical representation to provide context information. Then we turn that into language and we add other information and so on. Then after that, when the plan comes out, there is a plan post-processing. So there's another effort that makes sure that whatever plan comes out is sort of well defined. So we want to make sure that the reference labels are not broken. We want to make sure that the sequencing makes sense. We probably only want to execute the first N outcomes and not all the actions. Typically, there's issues with actions degrading rapidly over a longer horizon. And then all these papers also use downstream specialization, which is typically either supervised learning or reinforcement learning. And in our case, we used both. And from what I can tell, pretty much all papers instantiate this general recipe. But the problem is that if that is the case, it makes the claims in these papers very brittle because they depend very crucially on the LLM engine at the core. So, if you make any claims about things you can achieve, well, what happens if I switch out the LLM with a different LLM, right? Will your claims continue to hold? Or will they break apart? Or maybe the new LLM already takes care of whatever problem you were trying to address. So I find that a little bit unsatisfactory at the moment with some of these works. And lastly, and I think that's actually an interesting observation, which I find is not appreciated yet in many of these papers, which is that LLMs are not natively designed to optimize objectives for optimal control and decision-making. And basically what this means is LLMs are designed to optimize a word token prediction loss, basically, using internet text. But of course, that's not the same as the kinds of objectives that we maximize in optimal control. So for example, in reinforcement learning, most of the time we have an objective that looks like this. And this is to maximize expected discounted return. Of course, you can operate in, for example, robotic domains, then you have a cost and you would just invert the sign and it would look very similar, for example, in model predictive control. If you look at multi-agent reinforcement learning, then it's even more complicated. Now you have, for example, a Nash equilibrium where you're learning a joint policy where every policy is mutually optimal with respect to the other policies. So these are very well-defined objects that we're trying to extract, and they really mean something for us. We can write this down, and if we have an algorithm that is in some way rigorously guaranteed to produce these solutions or control policies, then we can have confidence that they solve the problem we care about. But I'm pretty sure that whatever the LLM engine is doing at the core of this recipe is not maximizing an objective that looks like this. It will be doing something else, and you will present some sort of demonstration that shows something fancy, but most certainly it's not something like this. And the fact is that I don't know exactly what it is that you're optimizing with your methods, which I think is problematic. Okay, so I think from there's potentially some interesting directions, and I'd like to get your thoughts on this as well. How should we move forward from here? One is we can continue to stick with this general recipe, right? We can instantiate that over and over again. We can chase the latest LLMs, and we can then hope that our claims will continue to hold in subsequent iterations. Probably not very satisfying. The other direction could be that we maybe try to retrain LLMs to maximize these control objectives that we really care about. But I've not seen a paper yet that tries to do this, and I'm wondering how this is even, how we can do this, how this would mess with the general knowledge base in these LLMs, and also, what training and how much extra training would be required. I think some interesting questions here. Or we could just dump LLMs altogether and create new kinds of large decision models or large control models. And I know that there's at least 2 companies that are now being created, one in the US and one in China, where they are trying to create this in the robotics space. They're having these very large exercises where they can collect a huge amount of data, and then they basically try to produce these kinds of models. So now we're looking at multimodal models, so not just text, but also other modalities like vision and sensing capabilities. We want to ask, where does the training data come from? Is it available for everyone? And how do we scale and stabilize the training? So I think there's lots of interesting questions here that we can explore. So that brings me to the end of the talk. Thank you very much for your talk, really, for your time. Really hope that you were able to extract some useful ideas from this. If you really like the talk and you want to hear it again, then you can come to the other talks. There will be in different places in London and also in various other places subsequently. So thank you very much for your time.